In this example, we're going to use a step-by-step method to find I0 for t that is greater than 0. From the solution to the first order differential equation, tau dy dt plus y that is equal to f. This differential equation has a solution of y function of t that is equal to k1 plus k2 times e to the power of negative t over tau. The principle of a step-by-step method is to find these three unknowns one by one. So we know that a k1 that is equal to the steady state value, k1 plus k2 that is equal to initial value, and a time constant tau decides how fast the signal decays. So step 1, for t that is equal to 0 minus, find Vc 0 minus. Let's draw the circuit. We have Vc 0 minus. We know that Vc 0 minus is equal to the voltage share of this 2K and 4K resistor. That is equal to, we can use the conclusion from chapter 2, voltage divider circuit. So we have 2 plus 4 over 2 plus 4 plus 2 plus 1 times 12 volts. That will give us 8 volts. Step 2, we're going to find the initial condition of I0 0 plus. From the continuity property of the capacitor, we know that Vc 0 plus that is equal to Vc 0 minus that is equal to 8 volts. Let's draw the circuit again. For t that is equal to 0 plus, we know that the switch is closed. At the same time, the capacitor can be represented by a 8 volts power supply. Pay attention to the polarity of a Vc we define. Draw the circuit again. And we know that this is a Vc 0 plus. It can be represented by a power supply of 8 volts. This branch that is closed, 12 volts here. And this is a current I0 0 plus. And we can find I0 0 plus by using Ohm's law. We know the voltage applied on this branch, that is a Vc 0 plus. So I0 0 plus that is equal to Vc 0 plus divided by 2 plus 4, which give us 4 over 3 milliamp. So we already find the initial condition. We have one equation that is k1 plus k2. We still need to find the steady state value. Step 3, find the steady state value I0 infinity. So we know that as time goes by, when t approaches infinity, this capacitor will become an open circuit. So let's draw the new circuit. I0 infinity. And since this branch that is shorted, we know that I0 infinity that is equal to 0. And step 4 is to find the time constant tau. To find the tau, we can use the conclusion that we got from Thevenin equivalent method. From the Thevenin equivalent method, we know that if the rest of the circuit can be represented by the Thevenin equivalent, and this circuit will have a capacitor. And we know the time constant tau that is equal to RTh times C. Since this circuit only have independent power supplies, we can find RTh by setting all the power supply to be 0. So that we can find RTh from this resistor network. Then RTh that is equal to this branch 2 in parallel with 2 plus 4, that is 1.5 kilo ohm. Then we can find the time constant tau that is equal to RTh times C, that is equal to 1.5 times 10 to the power of 3 times 100 times 10 to the power of negative 6. So that is 0.15 second. Step 5, I'm going to draw the conclusion. We already know that K1 that is equal to the steady state value I0 infinity, which is equal to 0. And K1 plus K2 that is equal to the initial condition I0 0 plus that is equal to 4 over 3 milliamp. And a time constant tau that is equal to 0.15 second. We can further solve for K2 that is equal to 4 over 3 milliamp. Then I0 as a function of t that is equal to 4 over 3 times e to the power of negative t over tau for t that is greater than 0.